Hello everyone, welcome back to Deeksha Karnataka YouTube channel. Your midterm exams will start soon, so here we are going to discuss all chapters that are important for your midterm exam. And first video will be on the theory of the chapter. Second video will be MCQs from the same chapter, so wait, don't go anywhere. After this theory revision is over, we will be having MCQ just after that. Then there will be another separate video for 2-3 markers. Now if you are only want to do MCQs, that is also available to you. If you only want some 2-3 marker questions practice, that is also available to you. Now here I am going to discuss the theory of the chapter. Lot of you have requested in the past, sir, please do the theory revisions. So here we are going to do the theory revisions very quickly, not in elaborate way, because we are anyway going to do all the important derivations, all the important questions and answers in the specific question answer format. But the main important concepts that you have to understand, so that in case some in-depth question comes from this chapter as a 1 marker question, or some unexpected question that might come from your paper, that you will be prepared to answer. So that's why theory revision, in my opinion, is very important. So let's start with the chapter list of the important concept from the chapter. Electric charge and properties of charge, obviously super important. Coulomb's law is very important. We have electric fields and field lines. Next we have electric dipole and dipole moment, and last but not the least, electric flux and Gauss's law. So these are all the important concepts from this chapter. So let us start with the first concept, which is electric charge. So there are two types of charges. Obviously we already know that there are two types of charges. What are those? Positive charge and negative charge, right? So positive charge and negative charge are the two charges. Next we have like charges repel each other and unlike charges attract each other. This is also fact, that if two positive charges are kept near each other, they will repel. If a positive and negative charge are kept near each other, they will start attracting, right? Next, in a neutral object, positive and negative charges are balanced. So if the object is neutral means apparently it does not have any attractive or repulsive property. For example, the chair, the table, the pen, the book from where you are studying, or the mobile phone from where you are studying, or laptop. So basically that is a neutral object by default. Okay, so that means the total number of positive and negative charge in there are balanced. Next is, to charge a neutral object, we need to add or remove electrons. So only electrons can be removed. Okay, to charge an object, we have to either add electron or remove electron. Now electrons are negatively charged. You already know that electrons are negatively charged. Now what is a positively charged particle? Positively charged particles are protons. In detail we will learn about that in our atomic theory chapter, right? If electrons are added to a body, it gets negatively charged. Okay, so if you add some electron to a body, it gets negatively charged. If electrons are removed, the body becomes negatively charged, positively charged, sorry, it will be positively charged. Okay, if you are removing electron, that means you are removing the extra negative charge, and the body will now be a positively charged. Okay, so if you add electron, it becomes negatively charged. If you remove electron, it becomes positively charged. Gold leaf electroscope is a device that can measure the presence of charge. It is very important. It cannot measure the quantity of charge, it can only measure the presence of charge. So if an object is charged or not, for example, if I want to test if this pen is charged or not, for that I have to use a gold leaf electroscope. If I brought it near the electroscope, if the leaves repel each other, the gap increases, that means we will say this object is charged. If it remains unchanged, unaffected, then we will say that body is not charged. Okay, there are a lot of experiments you might have done in your school life, preparing a gold leaf electroscope in your home, right? Now let's move on. SI unit of charge is Coulomb, very important. And Coulomb is charge is not a fundamental quantity. Okay, it is a derived quantity. So dimension of charge is ampere A times T. Okay, A is for current times T. T for time, right? The definition of current, current is considered to be a fundamental quantity, not charge. So that's why the dimension of charge is A into T. Let's move on. Basic properties of electric charge. There are few basic properties of electric charge. Charges are additive in nature. Okay, charges are additive in nature. That means charges can be added algebraically. So if you are adding 2 plus 2 is 4. That is the algebra. 2 minus 3 is minus 1. Algebra means plus is always plus. Okay, plus and minus, it will be the sign of the bigger number and the difference between them, right? We already learned it in class 6th or class 7th. So here we have one example. Q plus minus 2q plus 3q is equals to 2q. Okay, so you add the positive numbers. Q plus 3q is 4q, 4q minus 2q is 2q. That's how you can simply add or subtract charges. Okay, charge is a scalar quantity. From here also we get another sub property means which is not directly mentioned in the property, but you can derive it from the property that charge is a scalar quantity, right? Because if it is a vector quantity, you have to add them as a vectors, but here you can simply add them algebraically. Simply adding algebraically means it is a scalar quantity. Charges are conserved. What is the meaning of that? Total charge of an isolated system, very important. Total charge of an isolated system is always conserved. Isolated system means which is out of touch from entire world. So if you consider a box, if you leave that box as it is, if it is not interacting with anyone, then you can consider this box to be an isolated object. Okay, if you give some charge, say it has some charge q, no matter how much time has passed, no matter whatever happened outside, the total charge inside the box will remain same as it is. Okay, it will not change. Total charge will remains the same. It is not possible to create or destroy net charge carried by any isolated system, although the charge carrying particles may be created or destroyed. So you can create some, say, positive charge and some negative charge. It is possible. Okay, from energy we can create charges, but the net charge will remain the same. Even in one simple word, you can say the net charge in the universe is constant. Okay, you cannot create extra charges. If you create some positive charge, equal amount of negative charge will produce. Okay, there has to be equal amount of negative charge. Now charges are quantized. It is very interesting that all free charges are integral multiple of basic unit of charge denoted by E. What is E? E is the charge of an electron, and it is basically 1.6 into 10 to the power of minus 19. You can write it over here, 1.6 into 10 to the power of minus 19. If you want to download the PDF of this lecture, then don't forget to join our WhatsApp channel. The link of the WhatsApp channel is given in the description of this video. Also, if you want if you have not yet subscribed to our channel, don't forget to subscribe to our channel as well. We are going to do a lot more things in our channel in upcoming days, so don't miss out on that. Now any charge can be written as Q equals to n times E. What is n? N is an integer. N is an integer. Integer means 1, 2, plus 1, minus 1, plus 2, minus 2. 0 is also considered to be an integer. So any charge is always integer multiple of this factor. If you multiply, suppose if you see a charge saying 1.8 into 10 to the power of minus 19, is this charge possible or not? So you can see that this is not a integer multiple of this number. Okay, integer multiple means if you multiply this number with 1, you get this. If you multiply this number by 2, you get 3.2. If you multiply by 4, so forth and so on, right? But this number is not an integer multiple of this number, so this charge is not possible, right? So be careful, not all charges are possible. The charges has to be integer multiple of this number. E is the charge of an electron, and it is obviously 1.6 into 10 to the power of minus 19 Coulomb. Now very important concept, Coulomb's law. statement. The force acting between 2 point charges is, number 1, directly proportional to the product of the magnitude of the charges. Number 2, inversely proportional to the distance between the charges. The force acts along the line joining the two charges. Okay, so suppose we have two charges Q1 and Q2 separated by a distance small r, then from Coulomb's law the force between these two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance. Now sometimes in exam they will ask you that write this force in terms of vector form, write Coulomb's law in vector form. Okay, so in that case you have to add one unit vector and you have to change this form like this, F equals to, now remember that Q1 Q2, that is charge, is a scalar quantity, K is a constant, so from where, but force is a vector quantity, right? So you have to only one vector which is present in this configuration, which is the distance. Okay, distance is a vector quantity, right? So here you have to write this formula. This is a vector form of the same law. Okay, K is called Coulomb's constant. Its value is 9 into 10 to the power of 9, approximately the very standard value, Newton meter square per Coulomb square. Unit is also very important, and in terms of permittivity it can be written as 1 by 4 pi epsilon naught, where epsilon naught is permittivity of free space or vacuum, and its value is 8.854 into 10 to the power of minus 12. So this is something different, okay, and this is something different. Don't be confused between these two values, right? Now let's move on. Electric field. Now when we are talking about electric field is basically, first we will start with electric field due to a single charge. Okay, and then we will generalize it that even if only electric field is present, okay, there should be some source at a distance. We do not know about the source, but electric field can be treated independently. So that is the main idea. Main idea is that Coulomb's law talks about minimum two charges. If there are more than two charges, you have to take all the forces and add them vectorially. Vector addition is necessary, but it is sometimes becomes complicated to deal with all such pairs. Now if you know the electric field at some point, if there is a device which can measure the electric field at some point which is there, and using that field you can calculate force on any charge. That is the major thing. Okay, so electric field makes this Coulomb's law independent of the second charge. That is the basic idea. Okay, so here we have one small charge, capital Q, and we are trying to measure the electric field at a distance small r, and electric field is given by 1 by 4 pi epsilon naught Q by r square r cap. Electric field is a vector quantity. Okay, Q, so test charge is if you keep a charge over here, okay, then it will experience a force. Okay, if you keep a charge over here, that will experience as a force, and that force is given by Q into E. Okay, if a charge small q is kept inside the electric field E, then the force experienced by it is given by Q into E. Now why this is important? Why this is important? Because in most cases we do not know where is this source charge capital Q is located, but we know the electric field at some point. Okay, in many cases capital Q, determining capital Q is impossible. Okay, so if you can measure the electric field at some point, and if you keep a charge, test charge at a point inside that electric field, what force it will experience? It will experience a force Q into E. Now the electric field due to a system of charges exists at every point in three-dimensional space. So if you have a system of charge, single charge, double charge, multiple charge, does not matter. If it is a system of charges, electric field will exist in all the points around in three-dimensional space. For a positive charge, the electric field will be directed radially outwards from the charge. Okay, so positive charge, it is radially outward, positive charge radially outward. For a negative charge, electric field vector at each point radially inward. So if the charge is positive, electric field will be radially outward. If it is a negative charge, it is radially inward. Electric fields are radially inward. Okay. Electric field due to a point charge is spherically symmetric. So if you draw a sphere, electric field will be same at that each and every point on the surface, magnitude wise. So electric field is spherically symmetric due to a point charge. A positive charge experiences a force in the direction of the electric field. So if you have an electric field, okay, like this, and if you keep a positive charge, it will experience a force in the direction of electric field, and for a negative charge, it will experience a force in the opposite direction of the electric field. Okay, so positive charge experiences a force in the direction of electric field, and negative charge experiences a force in the opposite direction of the electric field. For example, if I ask you to study physics, if physics is something that you hate, okay, you will move opposite to the towards physics. I will not study physics. And if you someone who is liking physics, okay, sir is teaching some physics or asking me to learn physics, I will go to slowly, I will solve more questions, I will study more, right? So that is the that is true for even in the charge world as well, right? So positive charges, they move in the direction of electric field, negative charges, they move in the opposite direction of the electric field. Now properties of electric field, tumba important topic. Field lines start from positive charges and end at negative charges. If there is a single charge, they may start or end at infinity. Okay, so field lines start from positive charge and it ends at negative charge. Okay, it is always true. Any field lines, okay, so field lines is basically the pictorial representation of electric field. So if you start drawing pictures of electric field, because electric field is something hypothetical, you cannot see them using your eyes, right? So you have to use some imagination. So that imaginary lines are called electric field lines. Now when you are talking about some imaginary thing, you have to give them some properties. They have to have certain properties, so that when you are drawing, if you are drawing, I am drawing, or someone else is drawing, their drawing should be uniform, right? That's why these properties are given to them, these lines. Okay, so that everyone draws in a proper way. So electric field lines will always start from positive, it will always end at negative, but if it is only single charge, it can sometimes go to infinity, okay, or it can sometimes go to infinity, or it can start from infinity and go come towards the charge. Okay, it can either go to infinity or come from infinity based on the nature of the charges, but normally it starts at positive, goes to negative. In charge free region, electric field lines can be taken to be a continuous curves without breaks. So if there are no other charges present, okay, then it will be start and end, it will be a continuous line. Okay, starting point and ending point, it is a continuous line. If you keep another third charge, then it will have some break. Okay, the electric field lines will have some break. So that's why it is a third charge we are not considering. Okay, charge free region is important. That means whenever there are no other charges present in between two charges or three charges or five charges, if no extra charge is present, then the electric field lines will be continuous lines. There are no breaks. Two field lines can never cross each other. If they did, the field at the point of intersection will not have a unit direction, which is absurd. That means if two electric field lines, suppose one electric field line is coming from this side, another one is coming from that side, and they are intersecting at some point, but this is not possible. Why? Because electric field lines, if you draw a tangent to an electric field line at any point, if you know the electric field line and if you draw a tangent on that electric field lines, that tangent gives the direction of electric field at that point. That is also a property. Okay, if you draw a tangent at any point on the electric field lines, that tangent gives you the direction of electric field, right? So this is the tangent that gives the direction of electric field at that point. Now if two lines are to be two field lines are to be intersected, then at the point of intersection you will have one direction as per this line, one direction as per this line, which is not possible. Electric field at a particular point cannot have two different directions, it has to be unique. Okay, so this is not possible. Electric field cannot intersect because two different direction at a point is not possible. Electrostatic field lines do not form any closed loop. Closed loop means what? If something, say this is point A, this is point B. Okay, you start from A, you go to B. Okay, and then you start from B and you come back to A. If this happens, this is called a closed path. Okay, if your starting point and ending point both somehow coincide, we say this is a closed path. For example, here as you can see, it started from A, it reached to the point B, but it did not stop at B. From B again it goes back to A. If this is the case, then we say this is a closed loop. Electric field starts at positive and it goes to negative or goes to infinity. Okay, but it does not come back from negative to positive. Okay, so that is not happening here. That's why electric field lines are open loops and they are not closed loops. We will study later on in the magnetic field lines are actually closed loops. Electric field in free space decreases as we move in the direction of the electric field lines and vice versa. What is the meaning of that? So if you move in the direct, suppose electric field lines are given to you, something like this. Okay, what will happen if you move in this direction? So suppose here we have a point A, here we have a point B, here we have a point C. Okay, so let's see. So what will happen if you move from A to B to C? Where will be the electric field be maximum? Where electric field will be the minimum? So as you are moving away from the along the electric field lines, if you are moving along the direction of electric field line, the electric field slowly decreases. So electric field will be maximum at point A and minimum at point B and somewhere between A and B at point C, because even though it is it appears to be something different, but if you consider this is to be starting point and if you are moving in the direction of electric field, this is the farthest point from the electric field line and this is the intermediate point. So electric field will be maximum for A and minimum for B. Okay. Now electric dipole, another very important concept. Two equal and opposite charges separated by small distance is known as electric dipole. Dipole moments. So two equal and opposite charges separated by a very small distance. Very small means micrometer, nanometer. That should be the distance level. Okay, it should not be centimeter or meter. It should be micrometer, millimeter. Millimeter still can be considered, but micrometer or nanometer should be accurate. Okay, so smaller the distance, better representation of dipole. Okay, equal and opposite charges, they are bound with each other. Okay, for example, the ions, okay, or say HCl molecule. Okay, so this can be considered negative, this can be considered positive. They have a very small bond length. Okay, bond length is not big. Now they are obviously not cancelling each other as well. They have a stable bond. So this can be considered to be a electric dipole. Now electric dipole moment is the product of magnitude of one of the charges and distance between them. It is a vector quantity. So what is dipole moment? Take magnitude of any one charge. Magnitude of one charge here, say Q. Okay, and the distance between them. What is the distance? Distance generally we represent with the value 2a. It does not necessarily to be 2a. You can express it using d, x, y, z, anything, but for our calculation purposes we generally use the term 2a. Okay, when we do the derivation in the third video of the day, there you will see that why this 2a is very, very important. So electric dipole moment is the product of magnitude of any one of the charges and the distance between them, which is given by P equals to Q into 2a n cap. Now here it is a vector quantity. What is the direction of the vector? Direction of the vector is from negative to positive. So n cap basically is a unit vector in the direction of the dipole moment. The direction of dipole moment is from negative to positive charge. So n cap is basically a unit vector in this direction. Small unit vector, only direction, no value, right? So n cap basically gives you the direction of the dipole, and it is from negative to positive. Very important point to remember. Now electric field due to a dipole. So electric field due to a dipole, there are two major points. One is on the axis of the dipole, which is given by 1 by 4 pi epsilon naught 2p by r cube. Okay, and it is a vector form. You can write it in scalar form as well. The derivation we will do in the 5 marker section. And for equatorial plane, electric field is given by minus 1 by 4 pi epsilon naught p by r cube. So you can see that if you represent in vector notation, for equatorial plane, the direction of electric field and the dipole moment, they are in the opposite direction, whereas in the previous case the electric field and the dipole moment are in the same direction. How I can tell that? Because there is a positive sign. No sign means positive sign. So electric field and dipole moment must be in the same direction, that's why it is positive. But here there is a negative sign. This negative sign represents that the electric field and the dipole, they are in the opposite direction. Okay, electric field and the dipole moment, they are in the opposite direction. Okay, so remember these points. Based on these you might face some MCQ questions. Now dipole in external field. So if you place an dipole in an external electric field, it will experience a torque. Okay, and that expression for torque is given by tau is equal to P cross E. Again, this derivation is important, we will do that. And torque is given by Pe sin theta. This sometimes is handy for some small numerical questions. Gauss's law, another important concept. So electric flask, what is electric flask? Suppose we have a surface. We have some surface, and through that some electric field lines are passing. Okay, it can pass normally, it can pass with some angle. Okay, so whatever is the dot product between the surface vector, surface area vector, and the electric field, that is called basically the electric flux. For electric flux, the area is very, very important. So electric flux is given by E delta S cos theta. So if area vector is in this direction, okay, suppose area vector is some other direction, and the angle between the area vector and the electric field vector is theta, then this is the formula for electric flux, and it is E dot ds or E dot delta S. Statement of electric flux through a closed surface S is given by, this is the statement of Gauss's law. It says that phi equals to Q by epsilon naught or E dot ds. So phi is electric flux. What is the formula for electric flux? Electric flux is E dot ds. Now for complete surface you have to use a closed integration. Okay, it is a closed integration. Closed integral E dot ds equals to Q by epsilon naught. What is Q? Q is the total charge enclosed by the surface S. Suppose we have some charge, okay, Q, and we have a closed surface. Now remember, this surface can be anything as long as this is a closed surface. If it is open surface, Gauss's law is not valid. If it is a closed surface, no matter what is the shape and size of the surface, it is always valid. closed means, for example, the easiest answer of closed surface example is your pencil box. Okay, so if you are using a pencil box, if you open it, nowadays people use the chained pencil box as well, so you can consider that to be a closed surface. So whatever you keep inside the pencil box, that will remain inside, right? It will not automatically, it cannot go out, right? So unless and until there is a break in the pencil box. Now if there is a break in the pencil box, means it is no longer a closed surface, right? So for closed surface, this is the formula for electric flux. From this formula, for symmetrical surface, you can calculate electric field very easily. Okay, so there are few cases that also you have to remember. At first, few points from which you can expect some MCQs. Gauss's law is true for any closed surface, no matter what is the shape or size. Here Q includes the sum of all charges enclosed by the surface. The charges may be located anywhere inside the surface. Suppose this is the surface. One charge is located here, one charge is located here, another charge is located here, okay, another charge is located here. So what is the meaning of Q? Q is basically all the charges which are present inside the surface, but the charge which is not present inside the surface, we will not consider that charge. We will only consider the charge which are present inside the surface. Okay, so phi equals to Q by epsilon means this Q represents only the charges which are present inside the surface. Okay, electric field is due to all the charges, but Q is only for inside the surface. Okay, so that E dot ds, when I say E dot ds, okay, equals to Q by epsilon naught. Okay, this electric field is due to Q1, Q2, Q3 as well as Q4, but this Q, interestingly, is only the inner charges. Okay, that is very interesting part of Gauss's law. The surface that we choose for the application of Gauss's law is called Gaussian surface. Gauss's law is often useful to calculate the electric field for symmetric surface. Okay, because integration is involved. So if you see any kind of integration, that means uniform surface or symmetric surface is very essential to solve that integration quickly. If it is some complicated surface like this, you can still do the integration, but it will be complicated. You have to take small areas, small space, and manually doing will be not possible. You have to use some computer. You can put this into a computer and it can do the integration for you. That is possible, but humanly it is very difficult. Now here are the applications. There are mainly 3 applications, and now out of these 3 applications, this derivation is very important. Field due to an infinitely long straight uniformly charged wire. Electric field is given by 1 by 4 pi epsilon naught 2 lambda by r. Okay, and here is the line. As you can see, it's a line charged. Line charge means any pencil, you can consider a pencil, very long pencil, and each point of the pencil has some charge on it. Okay, and that charge, if you take any 1 meter of that length, and whatever charge is that 1 meter, it is called charge per unit length, which is represented by this lambda. Lambda is line charge. The fancy name is line charge density. Okay, but fancy name, we are not after fancy names. The meaning of this lambda is basically it represents charge per unit length. Next is field due to uniformly charged infinite plane conducting sheet. If it is a uniformly charged plane conducting sheet, the electric field is given by sigma by 2 epsilon naught. Okay, field due to a uniformly charged thin spherical shell. Outside the shell at any point, shell means it's like egg. okay, or you can consider a plastic ball. Inside the ball it's completely empty, like a air only present, right, but the hardcore material is present as a ball that you can see, or you can consider it to be a football, okay, or you can consider it to be egg, but you have taken everything out of the egg, only the shell is present. That is called shell. Shell means the cover. Shell means cover. Okay, so spherical shell means inside is vacant, nothing is present. So it's a charged shell, means the charges are present on this shell only. Okay, nothing is present inside, nothing is present outside. Okay, so this is considered to be a charged spherical shell. So for charged spherical shell, if the total charge on the shell is Q, then outside the shell the electric field is given by 1 by 4 pi epsilon naught Q by R square. And inside the shell, if you consider any point inside the shell, electric field will be 0. Okay, Gauss's law states that E dot ds equals to Q by epsilon naught. Now if you consider any Gaussian surface inside the shell, then there will be no charge included, so electric field will be 0. This derivation also sometimes comes, so you have to practice this derivation as well, right? And we will be doing that in our 5 markers, 2, 3, 5 marker section in the respective video. Now there is a comparison of electric field, how electric field changes with distance from the center from the electric shell. Okay, so if you consider this is an electric field along the y-axis, distance along the x-axis, then up to radius r the electric field is 0. So 0 means electric field is along this line. Suddenly on the surface it increases to the maximum value and then slowly decreases, and at infinity electric field becomes 0 again. Okay, so electric field varies as 1 by r square. Now the same graph, same formula is applicable for a charged conducting sphere. Remember this, charged conducting sphere will also have the same formula. Why? Because charges on a conductor always resides on the surface of the conductor, no charge resides inside the conductor. We will learn about that property in the next chapter, but this is very important point to remember, because in Gauss's law application sometimes this question comes. All the charges, all excess charge will stay only on the surface of a conductor, even it's a full solid sphere. Even if it's a full solid sphere, if it's a conducting sphere, conducting means made of metal. Okay, conducting means metal sphere. Okay, metallic sphere. Okay, iron ball or say steel ball, if it is made of metal, okay, the same principle, same formula is applicable for conducting sphere as well. Both graphs and formulas, everything is same. Okay, so this is the end of this lecture, and I will be back very soon in few minutes with the MCQ of this same chapter. Don't go anywhere, and if you like this video, don't forget to give it a like and leave your comment below for any questions or queries. Till then, bye.